great pleasure to introduce Valerie Taylor, who's the Royce E. Weisenbaker Professor in the Dwight Look College of Engineering, Department of Computer Science and Engineering at Texas A&M. I've known her for quite a few years, and she graduated from the University of California with a PhD in 1991, and I took notice that that was 20 years after I got my PhD at the University of California. So I'm twice her academic age. She's a world expert on high-performance computing, and she's the executive director of a new center for minorities and people with disabilities in IT, commonly called Commandit. And she's received numerous awards for her work as a researcher and for her outreach work. And I won't go through them all, but I will mention that she won the 2002 CRA Nico Haberman Award for increasing the diversity in computing and the 2005 Tapia Achievement Award for scientific scholarship. So welcome, Valerie.
Thank you, Richard. Okay. So today I'm going to talk about the performance of HPC applications on multi-core systems, and in particular looking at the projection. So this is the work of my former student, Sami Shikari, who's now working with IBM. And it's a reflection of a joint collaboration with IBM in Austin that includes Steven Stevens, Don DeSoto, and Raj Panda. So just to give you a little background about myself, so I do work in performance engineering. And so we've developed a system called Prophesy. And what Prophesy is a system to help to do modeling of high-performance computing applications on parallel systems. And so it includes an extensive database to actually archive the performance data, as well as different methods to do the modeling. And Prophesy is being used with a new project that's funded by NSF called Mummy. And it's for multiple metrics modeling infrastructure. And Mummy is based upon, I know all these acronyms, so Mummy is based upon PAPI, and PAPI, so PAPI is the performance application, the performance API that's being developed at University of Tennessee in Knoxville, and that's with Jack Dungara and Shirley Moore. And so that gives you low-level interface to the performance counters. It's also a collaboration with Kirk Cameron at Virginia Tech that's doing PowerPack. And so PowerPack actually has instrumented systems to get at the measurements of power at the component level down to the CPU. And so we're developing this infrastructure to allow users to actually look at the trade-offs between performance and power. And so some of my other performance work has to do with dynamic load balancing for distributed systems, also looking at doing predictions for scheduling of HPC systems. But today, I'm going to talk about performance projections using benchmarks. Okay. So just to go over a little outline of my talk, so I'll give an introduction to actually lay out the problem, talk a little bit about the background in terms of the overall projection system, then give some actually results and go into some detail about what we do in terms of the projection, where we decouple it in terms of the computation, also the communication, and then bring it together to actually project the full application on we've been looking at multi-core systems, but to actually look at it when we're scaling up with different numbers of cores. And I'll talk about future work and some related work. And then I'll summarize and give a little bit of details about our joint work with Commandit, because Richard's actually the deputy director of Commandit. So just in terms of the introduction and the problem that we have, so we're looking at an HPC application where we have a base system. And then we have a target system that's actually available, but the target system is such that we have the benchmarks on the target system, but it's not available for us to run the HPC application. And so what we want to do is to look at our projection system where we have details on the base system, how can we project the performance of the HPC application on those target systems? And the target system, possibly in terms of not being available for execution of the HPC application, it may be that it's not available, it's not accessible. It may be a new architecture for which you do have some benchmark data, but it's not available for you to actually execute your application. Or you may use it in terms of procurement to actually say, if you have a number of architectures that you're considering for procurement, how can you actually nail down the list and look at those architectures that may be suitable for your applications that you're considered as important? So if we look at this, so we can look at it from two perspectives. We can look at it from the HPC vendors, and we can look at it from the users. With the vendors, it may be used to explore design trade-offs. It can also be used to explore trade-offs between current and future systems, and also current systems for which we have measurements that are available and it's limited. So this was, when we looked at it in terms of collaboration with IBM, it's looking at exploring different systems that may not always be available. And then in terms of the HPC users, as was discussed, it could be used with system procurement, but you can also look at it in terms of application refinement. Having some details where you're doing that projection can help you to understand the application in which you can go back and make that refinement. So the work that I'm going to present today, we haven't done the refinement. We've been focused on looking at doing the projection and what type of errors we get with that projection. So some of the requirements when we look at it, where we have the benchmarks and we have the HPC application in the base system where we can get detailed information, and we only have the runtimes of the benchmarks on the target systems. So some of the things we want to look at is that we want to have low overhead, if at all possible, so where our projections are not taking days to actually get the projection. We want to automate as much as possible, so it's not where a user has to go in and actually put in that much information about the application. And so we also want to capture some aspects about the microarchitecture with our target machine as much as we can. With the benchmarks, we want it to be a standard such that that way we can look at the fact that we have significant performance data about the target architectures. And we also want it to be scalable and cover a large number of applications if at all possible. So some of the challenges that we have is that if we look at current systems, they're actually complex and hierarchical. So when you're looking at multi-core systems, you're looking at the fact that you often have, within a core, you have sharing of different resources. Then those chips are actually grouped together to develop a multi-chip module, in which when you look at the multi-chip module, you're looking at what happens between the cores on the chip. You're also looking at what happens between the cores on multiple chips, and these networks have different performance. What happens between the cores when you go across multi-chip modules, and this may be across nodes. So you're exploring all of that complexity when you're looking at multi-core systems. And some of the challenges has to do with mapping between the base architecture and the target architecture and taking into account some of the differences. And so some of those differences, let's say if we have the Power 5 chip as our base and the helium chip in terms of a target, then we're looking at things such as the different number of cores on the chip. We're also looking at, in terms of the different sharing of the different, let's say the L2 cache, which may be shared in one architecture and not shared in another. We can also look at the fact that L3 may be off chip in one architecture, on chip in another. So these are some of the complexities that we're looking at. So when we start to talk about the application, we're looking at developing what we call an application surrogate. So with the application surrogate, we're starting off with an HPC application. We're looking at a benchmark suite. So with that benchmark, we only have the runtime data on the target machine. We have detailed data on the base machine. So a question that comes up is how can we look at some linear combination of the benchmarks to represent the application? And it's this linear combination of the benchmarks that we give the term surrogate. So in terms of the projection, just to go into a little more detail, so we have the HPC application and we have the benchmarks on the base machine. On that base machine, we can get detailed information that goes down to the hardware performance counters on the base machine for both the HPC application and the benchmarks. However, on the target machine, we only have the runtime data. We do not have performance counters for the benchmarks on the target machine. Again, it's only the runtime data. And the question that comes up is how can we use the information that we have on the base machine as well as that information we have about only the runtime of the benchmarks on the target to actually give us that surrogate, which can then be used to give us projections on the different target machines. So now to go into a little more detail with the projection system. So we look at the HPC application. We're dividing it up into the computation and the communication. We're doing the modeling, then grouping it back together. What happens when we do the computation, I'm first going to go into some detail about the computation projection when we're looking at one node. Then we're going to look at what happens when we actually look at the communication, where now we're looking at scaling up in different number of cores. We're going to go back and look at the computation when we scale up and bring it all together to actually represent the full application when it's scaled up. So now to go into a little more detail with the computation projection system. So again, and I'll go through this, we have the benchmarks. For the benchmarks, we're looking at it oftentimes on a single core. You can actually execute multiple threads, or in this case, we're looking at 2 threads on a core. So we can execute it in single thread or simultaneous multi-thread modes. So we're looking at both our applications, our benchmarks, as being executed in that mode, and we're also looking at our application as being executed in that mode on the base machine, and getting those details with the performance counters, and looking at the runtime of the benchmarks. So the benchmarks that we're going to use actually has to do with the spec CPU benchmarks, where we have 17 benchmarks in the spec CPU, and we decided to focus on the spec benchmarks because of the availability and the wide use of these benchmarks and coming out with new architectures. Oftentimes there's an abundance of data about the runtime of those benchmarks. And the HPC applications, we looked at a range of applications, and I'll go into a little more detail about those. So our base machine that we're using is an IBM Power 5 processor. Yes?
It seems like it might be really useful to run the benchmarks on different input sizes on different target machines. That might make the problem easier. Is that something you would allow yourself, or that you, I mean, it seems like based on the target machine, you're going to stress different parts of the memory system and so on in different ways, and you may not want to use the same input size on your host machine and on your target machine.
Right, so what we looked at in terms of like the spec benchmarks, where you're looking at a given input size, so we started with this work, we just used that same input size for our spec benchmarks. Some of the future work, we're looking at, can we actually use some different benchmarks that may stress the system in different ways that's more controllable. But for this starting point, we wanted to address the question first, what type of error do we get if we're just starting off using the spec benchmarks as given? And so I realize this is unreadable, but I just go into a little detail. So with respect to the performance counters, this is a list of our performance counters that, of course, you can read from all the way up there. But it's just to give you a full list of the performance counters where we have 6 groups of the performance counters, where one group is looking at CPI, another group is looking at stalls. We have another group of counters that's looking at our floating point, and that's group 3. Then group 4 is looking at some misses with our look-ahead buffers. Group 5 is looking at more in terms of our memory subsystem, like our L2 and L3 caches. And then we actually have group 6 that's looking at the memory bandwidth. So these are some performance counters that we actually use in terms of the analysis on the base machine. So now, to go into a little more detail about this in terms of the steps. So what we're going to do is to create an application model on the base machine and then adjust that model for the target machine, and then we'll use a genetic algorithm to actually give us the detailed performance model that we have. And what we're doing and what I'm going to describe in the steps is we're looking at giving the genetic algorithm hints so that we can get to a model in a quick way. So what happens is that we have our groups of metrics that we have, that long list of groups, where we actually had 6 groups of metrics in which we're getting the data for that counter. We normalize it by the instruction count. And so with our application counter measurements, we're getting that data for the groups. Then we can go into the groups and actually see which counters actually dominate with the groups. But we can also include architectural information, such as how much time does it take to do different floating point operations, and how much time that it may take in terms of doing different MIS, in terms of the different levels of the memory hierarchy. And so that information, the architectural information, is represented in our coefficients A, the A sub i's for the different groups. Then what we're doing is we can take that A sub i's and we can actually generate a rank in terms of which groups actually contribute most in terms of the runtime. So with that particular rank, it gives us an idea in terms of the application. It gives us an idea if we're talking about something that's compute bound, something that's memory intensive. So it gives us some characteristics about the application when we can rank those groups. So this is an example with the AMBER application, in which AMBER is a quantum chemistry application. And so we can get the detailed information about the groups. And for AMBER, what we found in terms of the base machine, and I'm just giving the rankings, group 2 actually is ranked 1, and that actually has to do with some of the stalls. Then we have group 1 is ranked number 2. Group 3, which actually relates to your memory in terms of the L2 misses, is ranked number 3. So we can get an idea that this is more memory intensive. But that may not be the case on the target architecture. So we also have to take into account how we're doing mapping on the target architecture. So here, what happens is that this, for the step 2, we're taking into account the target architecture. And the way we're doing that is that for all of our benchmarks, we can do an approximate equation to the runtime that's based upon the groups and the values of A sub i's that represents some aspects about the base architecture. And so we're taking the runtime now, and this is where we use the runtime on the target system. So we're taking the runtimes for our different benchmarks, and using those runtimes, we solve a system of equations to get our A sub i's for the target architecture. Then we're using that information to actually give us a ranking. We're using that information to give us a ranking onto the target architecture. So again, what we're doing, we're taking the base machine where we have the groups, we have the A's that are based upon the architecture. We look at just the run times of the benchmarks on the target machine, and then we're looking at those run times to give us some values, solving a system of equations, to give us the A sub i's for the target machine. And we have to do this for each target machine. And then based upon that, we can rank the group. And the reason for ranking the group is because that ranking is then fed into the genetic algorithm such that when we try to do a fit, we're fitting to the groups that match, that have the highest ranking first. So here are the values that result in terms of the target machine when we actually solve our system of equations. So we have the ranking on the base from the application. And now based upon these values, we get a new ranking for the target machine. And so we can see some changes where the memory, the group 5, which was ranked number 3 on the base, is now ranked number 1 on the target. And for this example, we're looking at the base being the P5 and the target being Cloverton. And Cloverton, the issue that comes up is that you have 4 cores to the memory, so it actually has half the bandwidth as compared to the P5. And so this ranking becomes really important when we feed it to the genetic algorithm. So for the genetic algorithm, what happens is that we're given a ranking of the groups now to the genetic algorithm that's based upon the ranking for the target machine. And so that genetic algorithm, what we're doing is trying to match to the group that's ranked first. So we have details of the performance counters for the application and also the benchmarks on the base. And we're trying to match, do a good match based upon the ranking. So we may do a good match with, for example, in this case with the amber, we're doing a good match to group 5. So we're first trying to match those counters. Then we'll go to the second group. And so that we don't take too long, we may just do the first 2 or 3 groups in terms of the matching. So this just gives an example of how we're trying to do the mapping with the genetic algorithm, where this example is just saying for 7 metrics, where here we have the combined surrogates, how we're just taking values based upon our benchmarks to map to those performance counters to those groups. So when we actually look at amber, what happens is that and these are the values that come up for the different A sub i's for CPI, for bandwidth, reloads, the floating point unit, the different groups. And so what we get from our genetic algorithm is actually the list of surrogates that we're using and the coefficients for those surrogates. We then scale it by the instruction count that we have and get the execution time now. That becomes our projection of the execution time it becomes our projection for the compute time of that application. And because here we're only using 1 node, it becomes the time that we're executing on 1 node on the target system. So if we look at some experimental results, so for our HPC applications, we're using AMBER, which is molecular dynamics. Fluent is a fluid dynamics. The Dyna, which is doing crash simulations. Star CD, which is fluid dynamics, CHARM, molecular dynamics, a GAME, which is quantum chemistry. And I'm sorry, I think before I said AMBER, quantum chemistry, when it should be molecular dynamics, and seismic, and also WRF. The systems that we're using in terms of doing the experimental results, our base system is the P5, and it's doing out-of-order execution. We look at projection also on a power 6 that's doing in-order execution. Also another power 6 that's doing in-order, and that was the P570. Then we actually look at, and it has a different memory per core. We also look at projecting onto the Intel Woodcrest that's doing out-of-order, and projection onto Cloverton. So if we look at some of the results, and this is only for the compute projection, and this is given an average over all of the applications and also gives a standard deviation, we can see overall we're less than 14%. But it's very interesting with Cloverton, which is where we have the very big difference in terms of memory bandwidth, that's where we have the largest error. And so we're going back to look at how we can better do that. But a lot depends upon, too, the benchmarks. And this is the case where we're starting to look at different benchmarks, but we're still seeing this through. We can see where Intel Woodcrest, the Power 6, the 2 Power 6 architectures, for those we were less than 10%. And now I want to go into a little more detail now with the communication projection. So here we have to look at different communication patterns. We also have to look at non-blocking MPI calls, and then overlapping communication with computation. So what I just presented was more of doing the compute projection, and now we're looking at the communication projection. And we're going to use a similar scheme, but the set of benchmarks will be different. So with the communication projection, so we do have execution on the base, and we're using the Intel MPI benchmarks. So we're executing the HPC application on the base for different number of cores and get information about the application in terms of how it's scaling in terms of the computation and communication percentages with different number of cores. We also get information about the message size and the number of messages that are being sent for different number of cores. When we look at the Intel MPI benchmarks, we're doing the same, where we're taking those benchmarks and executing them on the base machine for different number of cores. In terms of the target machine, that's where we're executing the MPI benchmarks on different number of cores on the target machine. So we do have to get information about the benchmarks for different number of cores. And so we can get target machine parameters and couple that with details that we have about the base machine. So again, the Intel MPI benchmarks capture different communication patterns, being both point-to-point as well as collective. And so we're doing the measurements for different message sizes because that's occurring as we scale with different number of cores that we're using. So here we're executing it on the base. We're getting those values across the different number of cores. And then we're doing the same on the target machine. And so what happens is that we also have to calculate wait time. And so the way we calculate the wait time in terms of the application is to look at how much time it's taking overall in terms of its communication on different number of cores. We know how much time it takes for similar type of MPI calls or routines on the base, and we can subtract that to get a wait time estimate on the base machine. Then what we do, to look at that projection on the target, we're actually doing a projection of the wait time on the target, similar to the way we did the projection of the compute time. So we're getting a projection of the wait time on the target, and then we're using the message count, message sizes, and the information about the benchmarks on the target to give us the transfer time. Okay. So if we start to look at in detail some of the HPC applications that we're using for the compute, for the communication. With the communication, again, we're using the Intel MPI benchmarks to give us a projection of how the communication behaves on the target. The one thing we have to do is to project the wait time. And that's where we're using a similar scheme to what we did with the compute time to project that wait time. Because we look at the wait time as being attributed to the load imbalance that can occur, and that's actually a reflection of doing different load or different compute times. And so when we look at what happens when we actually do this projection of now just the communication, we're looking at using the NAS parallel benchmarks, but we use the multi-zonal. And the multi-zonal are hybrid. They're using MPI and OpenMP. The reason for doing the multi-zonal is actually long-term in terms of the work. So our initial work is starting off with MPI. Our future work that we're doing now is to explore looking at OpenMP and doing the model with OpenMP, and then going the next step to do the hybrid. So we did start off with the multi-zonal. And what we're doing is the target, again, the base machine is a Power 5 architecture, and it's the architecture at Texas A&M. And we're projecting it onto a Power 6 and also a Blue Gene, so we can have very different architectures. So when we actually look at the BT results, so with these particular results, you can see where it's giving you the percentage error. Well, we've actually broken up the error in terms of a multi-send and receive, and this is actually a non-blocking multi-send and receive. We've also looked at broadcast, reduce, and then the error with the overall communication. And you can see here the overall communication error is really attributed to the multi-send and receive, which is doing the non-blocking. However, it's the case that most of the error is, well, all of the error is less than 16%, most are less than 14%. When we actually look at the Power 575, again, most of the overall communication error is due to the multi-send and receive. When we actually look at the LU, we're seeing very similar, where very little of the error is due to the broadcast or the reduce. And then with the SP multi-zonal, we see very similar. And so we can actually see with the communication, where we're starting to focus some of our work now is to do better predictions with the multi-send and receive. But we still look at being less than 15% is really good in terms of doing the projection on a machine for different applications where we don't have access to the machine. So now we're looking at what happens when we integrate communication and computation. The one thing we do have to take into consideration when we do that is what happens with hyperscaling. Because when you actually look at what happens on parallel execution, oftentimes you end up with hyperscaling where when you scale up to large enough number of cores, the memory is such that, or the data footprint is such that you don't have to use a lower level of your memory hierarchy. So it's possible now when you scale up, instead of using L1, L2, L3, you now only have to use L1, L2, which gives you hyperscaling. So we want to do some analysis about the application in terms of looking at the compute with the application and scaling up to determine where this actually occurs. So if we start to look at the combined performance projection, what happens is that, again, we have the HPC application that's executed on the base, And so when we look at that execution on the base, we're doing a couple of things. We're getting the MPI profile, but we're also getting information about the performance counters. The counters that we're paying attention to now has to do with group 5. So those counters are such that it tells us information about how much accesses we have to the different levels of your cache. And so we can actually see what happens when, and look at that trend with those detailed counters to determine what's occurring as we actually execute on different number of cores. And so actually, just to give an idea, with a different number of cores, we started to look at about 4 to 5 different configurations of cores. Okay. So we're getting details about the hardware performance counters that gives us the cache strong scaling model, because we have a fixed size problem that we're scaling to different number of cores. Then we're also using the MPI information about the application to give us the actual communication and also to give us details about the compute scaling as well. And so we start to use that to project the application communication performance and the compute performance, because we need this information also to give us a projection too about wait time as well. And so then we can project onto the HPC application, onto the target system. So just to go into a little more detail, with the compute component scaling model, so here's where we're looking at the ratio between computation and communication, so we'll know how that scales, and looking at the scaling factor with the computation. When we're actually looking at the cache scaling model, that's where we're looking at the issue to actually determine when we have hyperscaling. And that's where we're looking at the counters from the 5th group to give us details about what's going on with our different levels of cache. So then the two actually combine to give us now, we're looking at what happens when we project the performance of the application for different number of cores. So we've gone through thus far to say we did the compute projection, and that was one node. We looked at the communication projection, and that was different numbers of cores, but the communication, and we had to also project that wait time. And now we're looking at what happens when we combine the two. We have to also look at issues about hyperscaling. So again, to give some details in terms of the performance, so we're looking at our multi-zonal, but we also went back to look at Amber and different classes or different input sizes, and we actually give the communication percentage. And we're also looking at games and WRF. In terms of the systems that we're using, again, the P5 at Texas A&M is our base. We're projecting it onto a P6 and also a Power PC 450, and then the Intel Xeon. So we're looking at the Blue Gene as well as an Intel, just to give us difference in architectures. So if we start to look at the results that occurred, for the block tridiagonal, the multi-zonal, we can see what happens in terms of the combined projection, where in all cases we're less than 16%, which is really good. If we can actually see where that error is coming from, we can see the two areas that it comes from has to do with the computation, and in some cases this point-to-point, and we can see that with the multi-zonal. When we actually get to Amber, we're seeing a little different, where here with the combined projection, most of it is due to the errors with the computation, and some is doing actually into having to do with the collective communication in terms of the error. But we do see the major error as being attributed to the computation, but again, it depends upon what's that percentage of computation to communication. Okay. And actually when we scale out. So here we're scaling out to 1,024 cores. And then if we also look at the amber, the factor IX results on the blue gene P, we're seeing a little different where, again, so we're focused on the computation, and that's actually an area of future work. But here we're starting to see, in terms of the errors, mainly attributed to the computation error. And then we can see with games, we're seeing a lot of error in terms of both the non-blocking and the blocking, so it's ranging across all of the different types of communications when we have games. But we're seeing error that's less than 16%. Okay. And now to talk a little bit about some of our future work. As we discussed, some of our future work is focused on extending this work, so now we can see that we address the question of if we have only benchmarks on target machines, and those benchmarks we use the spec benchmarks and the Intel MPI benchmarks, and we don't run the HPC application on those benchmarks, on those target machines, but we do have detailed information about the benchmarks and the HPC application on the base. How good can we do with projecting the performance? And we can see that we were less than about 16%. In terms of the future work, our current work focused on MPI, and what we're starting to do is work related to OpenMP. And looking at OpenMP allows us to also extend that work to working with hybrid, because then we can work with MPI and OpenMP type applications. And so the OpenMP projection will entail similar analysis to what we did with the Intel MPI. And then some of our future work, so again, that has to do with the hybrid of combining MPI and OpenMP, because we've seen results where the hybrid actually performs better than just doing MPI, especially when you have multi-cores. And extending the work to actually look at different ways to characterize architectures. And that's looking at different benchmarks that we can do that we can actually change in a controlled manner so that we can explore different architectural features. So in terms of related work, there's been a lot of work in terms of using surrogate-based projections. And so some of that has to do with actually requiring to execute the HP application on a system. And so we only executed on the base system. Some we've seen to execute it on the target, but maybe small numbers of cores. Or it may be where part of our work had to do with how we're doing the weighting of the groups. Because with the weighting of the groups, we found that to be a critical factor in terms of developing the actual model that's generated from the genetic algorithm. So having that ranking allows the genetic algorithm to match to the hardware counters that are most critical to the application when you're looking at the target architecture, and that becomes important. And then if we look at it, the separation of the communication and the computation allows for maximum scalability, because then we can explore different features about each one than if we tried to do it combined. And so if we actually look at it, there's been some work also with looking at just memory-bound type applications. And our work is actually exploring a range of applications, both compute-intensive and memory-intensive. There's been some work in terms of different tools, like the Phantom tool with Jai, which actually is looking at some simulations, because you actually have to replay. And that's important, and you can end up with high accuracy, but you end up with a large overhead in terms of having to do the simulations. There's also the work with Alan Snavely out of UC San Diego of using MPI traces and predictions. But again, there's simulation being used, and a lot of that work is focused on looking at the memory and understanding the memory in detail. And so there's other simulators like the MPI Sim and also the MIMAs. And so again, it goes back to our goal was not to utilize simulators if we didn't have to. And so that was a major goal. Then there's also the work out of Hammond, out of the UK with the WARP simulator, and that entails model construction, machine benchmarking, but it also includes the simulation. And then there's also some work that Alan's been doing with performance prediction, but again, part of it includes having to work with MetaSim. So if I summarize about our work, is to look at finding as accurate as possible an efficient method to actually do the projection of an HPC application onto a target machine where we only had benchmark data. And so, well, we only had that benchmark data in terms of execution time of the benchmark data on the target machine. It's not where we were executing the HPC application on the target machine. And so the question that we wanted to address is what type of error would we get, and then also what type of extensions and how can we address those errors. So this work focused on what type of error we can get, and we're seeing that we're in the range of less than 16%, and the overall average was 11.2%. which we find really good. And so we're looking at extending this work in different ways in terms of the communication, as well as looking how we can do better with the compute, and also looking at the benchmarks that we have. But working with the spec benchmarks, the spec CPU, gave us that overall average of 11%. So I now just want to introduce the Center for Minorities and People with Disabilities and IT, which in addition to doing research, I also do outreach. And so this center is a new center. It's a nonprofit organization in which our goal or our vision has to do with contributing to the national need for an effective workforce in computing and IT through synergistic activities related to minorities and people with disabilities. So it spans across all, and looking at the common area has to do with cultural component, and it's a cultural to understand ethnic minorities, a cultural component to understand disabilities and be engaging. The executive committee includes also Janine Cook, who's at New Mexico State University and also a PCASE recipient, Ron Eglash, who does a lot in ethnomathematics, bringing culture into the teaching of mathematics, and Bryant York, who's a Haberman recipient, Tappy Award recipient, and ACM Fellow, and Richard Latner, who's a Haberman recipient, Passman recipient, ACM Fellow, and IEEE Fellow. And some of our activities, we look at twofold, that is promoting innovation that enriches the community, as well as looking at ways to increase the engagement of minorities and people with disabilities in IT. In terms of the engagement, we have activities focused on professional development. We also have a funded project to look at taking ethnomathematics or culturally situated design tools into boys and girls clubs. Also a video archive or a video gallery of researchers that can serve as role models. And then a student competition where students actually propose projects for introductory computer science courses that are engaging for ethnic minorities and people with disabilities, in which we're reaching back to the community. We also have what we call diversity as an innovation resource, where we're looking at leveraging projects nationwide that are engaging for minorities and people with disabilities, to look at those projects as being focused and working on a societal problem. And a societal problem has to do with math education delivery for middle school students in underserved communities. We also looked at graduation statistics, and we have an e-newsletter that comes out every 2 months. So with that, I'll say thank you and questions.
If you look at the For instance, in a memory-bound application, I can imagine if you have measures for cache misses and memory access, and you translate them to another machine, you get a very precise measure how fast it takes. If you have the times, how fast the different caches are. But the question is, how can you translate the number of cache misses if the caches are larger and if you have a different associativity? And so these are the harder numbers to reach, in my perspective.
Right. So what we're doing, it's not where we're translating one-to-one like cache misses. You're translating it implicitly, and that is you're translating it through the execution time of your benchmarks. So you know the execution time of your benchmarks on the target machine. And so if some of those benchmarks are also memory bound, you'll see that change in terms of different features about the architecture reflected implicitly in the execution time. And so that's where we're getting it implicitly through the execution time of those benchmarks. And when we go back and get the A sub i's that have the hash mark, that's where we're getting those A sub i's to reflect different architectural features of the execution time on the target through the benchmarks. So we're getting that implicitly, okay? And then what we do is go back and using that information, we can actually identify the groups that are important. So the memory group will be important, and we'll try to match in the genetic algorithm, match the HPC application to those benchmarks that have similar type of characteristics. And then that, let's say if it's an increase because of some aspects about the cache that's changed that causes the execution time to increase, it's going to be reflected in those benchmarks.
When you make your projection, did you find any bias in the sense that all computation projections were optimistic and all communications were pessimistic and so on?
No, we did. It's not where we could make the general statement. What we did find when we actually looked at the full projection, that over probably about 54% were over projection. So we overestimated in terms of the execution time.
In the middle there, yeah.
If some company today wants to, say, run some HPC application, how do they figure out which systems to procure or run it on today? Do they just kind of guess, or do they use some method like you mentioned in the related work? Or would a system like yours that has 11% or 16% error be a big help to them?
So, and actually we're collaborating with like Argonne National Labs, where the issue that comes up, you want to do that projection onto different systems. But one question that Argonne is trying to address is what happens, how do you understand different configurations? So for example, you know the architecture, but a question that comes up is what should be the memory subsystem, what should be the storage subsystem, how much memory, how much storage. And so when you actually start to look at those different configurations, for our system, we would need to have benchmark data on those different configurations, and then it would be useful. And so what we're trying to do is to extend the work so it becomes useful for where you have different benchmark data, because you can go in and now pare down your list of what architectures you may want to consider based upon some initial projection. But what we're starting to look at is when you're looking at different configuration, if you have a set of benchmarks for which you can actually you can control the knobs on the benchmarks and explore different architecture features in a better way, it'll help you in terms of adjusting the configuration, because now you know some extremes. And so then it can pare down that space to say maybe this space is a sweet space instead of the whole space that you're exploring with different configurations. So this work becomes some work that you can build upon to actually explore that different configuration. And can I just add one more thing?
Yeah, go ahead.
Some of the things that's actually done now for large-scale procurement is that you may actually give a class of applications to different vendors to actually look at running across those machines and get data back. Okay. But that takes the people power at those different vendors to actually give you that information back.
Thank you very much.
Okay.